Let's get started with our lecture for today, which is about harmonics elimination and filter design. Now, if you remember last time, we talked about the three-phase inverter, single-phase inverter, and we said that usually we can obtain a square wave like this, okay? And we said this square wave has loads of harmonics, right? We said we have the fundamental frequency. Okay, if we try to draw this one, you'll find that we might have DC component, which means the zero frequency is at some value, which is the DC component. We have the fundamental frequency, which is the 50 Hertz frequency. And we said we have the, of course, the even harmonics cancel each other. So we have no even harmonics. We have the third harmonic, the fifth harmonic, seventh, and so on, right? But the problem here, if the difference between the first harmonic and the third and above harmonics, if the difference is not very high, like if the third harmonic is very close to the first harmonic, we will find difficulty to design a filter, a proper filter. Or we need a large filter to cancel these harmonics, the third, fifth, and the seventh. Okay, so usually we use a low pass filter, and this low pass filter should be able to allow the fundamental frequency to pass and reject the third, fifth, seventh, ninth, and so on. Okay, so what we need to understand here in the harmonics elimination is, in addition to the filter design, in addition that we need to design a proper filter, also we have the option to not include the third harmonic, fifth harmonic, seventh harmonic from the beginning. Okay, so we can easily, in such way, we can eliminate the third harmonic and use simple filter to cancel the fifth, seventh, and so on. We can use simple filter, low order filter, not high order filter, not very complicated filter, and also a cheap filter. Now, coming back to the Fourier series, we said that this square wave, which is usually we can obtain it from the output from of the inverter, is equal to how much? We said this is if we said that this is V of t, so this will be equal to A naught over 2 plus the sum for A n cosine n omega t, where n from 1 to infinity, plus sum for Bn sine omega t n omega t, where n is from 1 to infinity. And last time we said that A naught is equal to 0, right? An is equal to 0 for a square wave like this, and Bn is equal to 0 for even ends, for even harmonics. And finally, we have only one value for Bn when the values are odd. So we can say that Bn is equal to, we said 4 over pi integration from 0 to pi over 2, because here we have symmetry, right? Pi over 2, this is pi, 2 pi. So we can just take this portion integrated, multiply by 2, right? So this is 4, instead of 1 over pi over 2, this will be 1 over pi over 2 times 2, right? Integration from 0 to pi over 2, so this is V maximum sine n omega t d omega t. So this is VBN. We substitute our values. We find at the end that Bn is equal to how much? For V maximum over pi n. Okay, and this is only for odd harmonics, for the first, third, fifth, seventh, ninth, 11th, and so on. So this is the definition for the square wave from Fourier series. We can easily take this one, substitute it here in this equation. You'll find that Bn will be replaced by 4 times Vm over pi n, right, times sine n omega t, and all of this sum from n equal to 1 to infinity for odd values only. Now, in order to eliminate harmonics, we have an easy way to eliminate some harmonics, not all harmonics, of course. We can eliminate harmonics one by one, right? So instead of starting from 0 value here, we said that we can start the angle from alpha and make all these values from 0 to alpha to be equal to 0. And then find the value where this equation is equal to 0 and substitute by the value and get the value of alpha. Let's see how to do it. Okay, now we said for A naught, B naught, A naught, AN, BN is equal to 0, and then we can easily say that BN is equal to how much? 4 over pi integration. Now this integration, instead of from 0 to pi over 2, it will be from alpha to pi over 2. So this is pi over 2, this is pi, and this is here 2 pi. So we'll take the integration for this portion only. So this is from alpha to pi over 2 for V maximum sine n omega t d omega t. So this will be equal to 4 times V maximum over n pi multiplied by minus cosine n omega t from alpha to pi over 2. Now the new Bn is equal to how much? Is equal to 4 times V maximum over n pi times cosine n alpha. Okay, so this is the new value for the Bn. We need to think about this value. Now when this value equals to 0, we can say that Bn is equal to 0 at some points, right? When for V maximum over n pi cosine n alpha is equal to 0. When this equal to 0, when cosine value equals to 0, because 4 times V maximum will never be equal to 0. So here cosine, we need to find when the value of Bn equals to 0, when cosine n alpha is equal to 0, right? And this occurs at some points only, when n alpha is equal to how much? Is equal to 90 degrees, right? So we can say cosine 90 degrees is equal to 0. So alpha value can be equal to how much? 90 degrees over 3, right? So this will be 30 degrees. So if we start our square wave, if we try to use our modulation technique to start at alpha equals to 30 degrees, at this point we can eliminate the third harmonic. Okay, only the third harmonic. Now, if we try to, if you want to eliminate the fifth harmonic, we can say alpha is equal to how much? 90 degrees over 5. Okay, because n at this point is equal to 5. So this is 90 over 5. It's how much? 18 degrees. This method can be used only to reduce one harmonic at a time. Okay, we cannot, for example, we cannot reduce third and fifth harmonic. We cannot reduce fifth and seventh harmonic. No, we can eliminate only the third harmonic or the fifth harmonic or the seventh harmonic, and so on and so forth. What other harmonics here we can eliminate? Tell me. We can say n is equal to 7, right? Or 5 we said 18 degrees. N equal to 7, so this will be how much? 90 degrees over 7, and this will be 12.85 degrees. Here we can say 90 over 9, and this will be 10 degrees. Okay, we can start alpha at 10 degrees. Okay, so this is a very simple method, but also it's not that practical, because what we care about actually is to reduce the harmonics that are very close to the first harmonic, like the third and the fifth harmonic. Now the problem here in this method, you can, if you want to reduce the third harmonic, you'll start your waveform at 30 degrees. So almost half of the wave will be reduced. It seems not viable, not that very practical way, but maybe we can use it to reduce the 7th, 9th. That will be more practical. The other method, which is we can use this modulation, we can use what we call the bipolar modulation. This is a bipolar waveform, or a waveform comes from a bipolar modulation technique, because we jump from minus V maximum to V maximum. In this method, we can simply eliminate the harmonics by selecting the values of alpha here. We can select where we can chop our waveform. It's not just simply compare the sine wave with the triangular wave. No, of course, if we compare the sine wave with the triangular wave, we can obtain a bipolar waveform like this. But we can design the chopped pulse width modulated signal here in order to be chopped at certain frequencies, okay, at certain angles here. Let's see how can we solve this equation. Again, this waveform can be obtained from Fourier series, which is a sum of sine waves and cosine waves. And because it's a symmetrical waveform, we can see that A0, An are equal to zeros. Okay, at the end we have Bn, right? Bn also has even harmonics, cancel each other. Now we can say that Bn is equal to how much? 4V maximum over pi. Now here we can make integration for these values, okay, for these waveforms here. This is pi over 2, and that's what we need. The rest are like symmetric. This is symmetric to this one for the half waveform, so no need to make integration for all of them. So this will be 4V maximum over pi, integration from 0 to alpha 1. So I'll say this is alpha 1, this is alpha 2. The value here is alpha 1, and the angle here is alpha 2, and this is pi over 2. Now we need to make sure that when this alpha 1 and alpha 2 achieves Bn equal to 0. So we can say that Bn is equal to 4V maximum over pi, integrate from 0 to alpha 1 for sine n omega t, minus integration from alpha 2, from alpha 1 to alpha 2 for sine n omega t, d omega t of course, okay, d omega t, plus V maximum, which is outside here, integration from alpha 2 to pi over 2 for what? For sine n omega t d omega t. Okay? Make integration for this Bn. You will find that Bn in this case is equal to how much? 4V maximum over n pi times 1 minus 2 cosine n alpha 1 plus 2 cosine n alpha 2. Now this is the new equation for Bn for the bipolar waveform. Okay, now we can say that we can select alpha 1, alpha 2 to make sure that Bn is equal to 0. And since we have two values for alphas, so we can have two equations with two variables and obtain, like, eliminate two harmonics at a time. You can eliminate two harmonics at a time. Clear? Or you can select more alphas here from 0 to pi over 2. We can increase the number of chops here to make alpha 1, alpha 2, and alpha 3, for example, or alpha 1, alpha 2, alpha 3, alpha 4, and increase the values of alpha, the options here, so increase the orders. Instead of alpha 1 and alpha 2, instead of two variables, we will have four variables, for example. And at that point, we will have four equations with four variables. We can solve them and obtain, like, eliminate the third, fifth, seventh, and ninth, for example. Okay, so we can extend this equation. Instead of just using alpha 1, alpha 2, we can say that Bn, here we can say that Bn is equal to 4V maximum over n pi times 1 minus 2 cosine n alpha 1 plus 2 cosine n alpha 2 minus 2 cosine n alpha 3 plus 2 cosine n alpha 4, and so on, minus and so on. Okay, so this is the new Bn, and you can increase whatever you want, the values of alpha 1, alpha 2. Then we equate this Bn value, Bn equation with 0 and solve the equation. Okay, you'll get two equations with the two variables and solve them, or four equations with four variables, and so on and so on and so forth. Okay, so here we can simplify this equation to be equal to Bn for V maximum over n times pi times 1 plus 2 sum from k equals to 1 to m for minus 1 to power k, and here multiplied by cosine n alpha k. Okay, and these of course for odd ends, and alpha k from 0 to pi over 2. So we can use this equation and simply chop our waveform at certain frequencies, at certain angles, okay, at certain phases, and simply we don't include the harmonics from the beginning. And since, let's say for example, we eliminated third and fifth harmonics, we can use a very simple filter at the end. Yes, we have a waveform, a chopped waveform, but this waveform has the fundamental frequency plus the seventh harmonic, which is very far away, not very far, like far away from the first harmonic. So we can use a very simple filter, small filter, to reject these high order frequencies. Now let's come back to this equation here, this one, and try to eliminate the third and the fifth harmonics. So I'll select n to be equal to 3 and n equals to 5. What we'll do here to eliminate the third and the fifth harmonics, so we substitute by our equation Bn. This will be 1 minus 2 cosine 3 alpha 1 plus 2 cosine 3 alpha 2. This is Bn. We will equate it with 0 because we need to cancel these harmonics. And also the second equation, 1 minus 2 cosine 5 alpha 1 plus 2 cosine 5 alpha 2 is equal to 0. Now these are two equations with two variables, which are alpha 1 and alpha 2. We can solve them and obtain the value of alpha 1 and alpha 2, where we need to chop our waveform. But the problem with these two equations are they are very complicated to solve them by hand. They can be solved by iterations. Okay, like you need to use either simulation program like MATLAB and try to solve them. Of course, this task was very difficult in the past. Like you need to create your own program or something. But nowadays it's very simple. We can use MATLAB and solve these two equations. Here I put the code for you. This code, you can put the two equations here. You can define the function, okay, or the function f, the variable. Here I put the variable a, and I put alpha 1, alpha 2, a of 1, a of 2. This means the first variable and second variable of a, and draw these equations. We need to start with initial values. This can be obtained randomly, so I define the initial values of a naught, and also I'll use this function which is called fsolve of the function that is defined here, the two functions here, and the initial values. And this will return the values of alpha 1 and alpha 2. The MATLAB will solve it by iteration. So take random values and keep trying till you get the correct value. When fv equals to 0, the value of this equation equals to 0. Now, so you can use fsolve on MATLAB. What you need also is to install the optimization toolbox. If you don't install MATLAB with the optimization toolbox, MATLAB will ask you to install this toolbox to be able to use this function. I tried it yesterday and obtained alpha 1 to be 23.6449 degree and alpha 2 to be 33.3277 degrees. So here we can chop our waveform at 23 degrees, 23.6449 degrees, and this one here, alpha 2, at 33.3277 degrees. And here, of course, 90 degrees, or pi over 2. Clear? By this method, we are able to eliminate the two harmonics, the third and the fifth harmonic. Now, we can use other modulation techniques like the unipolar modulation or unipolar waveform. Let's see how to do this. For the unipolar, we can simply repeat the same procedure that we just used and say Bn is equal to 4 times V maximum over pi, but now the integration will be only for this portion and this portion. So this is alpha 1 and this is alpha 2. So we'll say integration from 0 to alpha 1 for sine n omega t d omega t, and plus integration from alpha to pi over 2 sine n omega t d omega t. Make this integration, you'll find that Bn is equal to how much? 4 times V maximum over pi times n pi, and this is multiplied by 1 minus cosine n alpha 1 plus cosine n alpha 2. Also, you can extend this for m pulses. If you try to extend this for m pulses, you'll find that Bn is equal to 4V maximum over n pi times 1 minus cosine n alpha 1 plus cosine n alpha 2 minus cosine n alpha 3 plus cosine n alpha 4 minus cosine, and so on and so forth. And this can be simplified to be Bn equals to 4V maximum over n pi times 1 plus sum for minus 1 to power k times cosine n alpha k, and k is equal to 1 from 1 to m. And these, of course, for odd values of n, right? And alpha k from 0 to 90 degrees, right? Okay, so now we'll try to solve this equation for two harmonics only, okay? For the third and the fifth harmonic, okay? Let's try to do this here. So again, we'll try to eliminate the third and the fifth harmonics by substituting by our equation that we just obtained. Here we have alpha 1, alpha 2, and this is pi over 2, right? So we can obtain two equations with two variables. So we can say 1 minus cosine 3 alpha 1, here n is replaced by 3, plus cosine 3 alpha 2, and this will be equated to 0, and here 1 minus cosine 5 alpha 1 plus cosine 5 alpha 2, and this will be equated to 0. Again, we can use the same function here, if solve on MATLAB, and obtain by iterations the values of alpha 1 and alpha 2. I also solved this one yesterday, and I obtained that alpha 1 equals to 17.8318 degree, and alpha 2 is equal to 37.966 degrees. Here, just make sure that if you write this one in the same script file, make sure that you define two different functions. Now, once we eliminated some harmonics, okay, we can use filter. Now let's see what are the considerations for the for filter design. Now this filter can be either a simple filter like a C filter, only capacitor, can be only inductor. So here we said like calculating voltage and current ratings of power devices, okay, depends on many factors. Depends on the inverter type, the inverter itself, either a single phase, three phase, current source inverter, or voltage source inverter, which means you want your inverter to act as a current source on the output or as a voltage source on the output, because this will be taken into consideration when you design the filter. What other considerations is the output impedance, of the inverter. Here we have also the what we call the modulation techniques like unipolar, bipolar, pulse width modulated waveform. Have you eliminated the harmonics or not? Also depends on the harmonics. What else? The load and the control method. So all these factors must be taken into consideration when you try to design your filter, or when you obtain the ratings of your components. Our design also requires to obtain the expression of the instantaneous output current. Either the current is it a smooth sine wave like this, or is it a square wave, or how it looks like. Okay, we need to make sure that we must be able to obtain the expression of the output current. Also, we need to obtain the current waveform for each device and component in our inverter. To reduce this harmonics, we need to design a filter. The filter is necessary, we said. Now we removed third, fifth, or seventh harmonics. Now we can use a wide range of filters, such as the C filter. Okay, just capacitor. This capacitor is very simple, but it draws more reactive power. So here we have some advantages and disadvantages. If you try to use LC filter, like this tuned LC filter, this is a band pass filter. You can only eliminate one frequency. Like this one, you can eliminate only one frequency because it's a band pass filter, or just a small band of frequencies. You can use LC filter like this one, or you can use CLC filter like this one. This filter can reduce the harmonics of a wide range of bandwidth, but it draws less reactive power. Very good. Now, these can be considered for the standalone inverters when you have a load and you want to supply this load. For grid-connected inverters, usually we prefer to use current source. We prefer to use inductor at the output, okay? So here, before going to the grid, we need to make sure that we have inductor before supplying the grid. So we can use L filter like this. This L filter has poor voltage regulation and it's bulky and costly. If you try to increase the value of the inductor, you'll find this is bulky inductor. The voltage regulation for this is not very good, but at the same time it's bulky and costly. What we can do actually to use LCL filter. LCL filter, we can use small values for the inductors, and in the middle we can use capacitor to reduce the to enhance our filter. At this point, we can provide a similar attenuation effect with smaller inductance, and then we can have a smaller size and less cost for our filter. These are general types of filters that we can use in inverters. Now let's jump to solve one example. The example says, we have a single phase inverter, and this inverter is supplied by 220 voltage DC input, and the inverter frequency is 50 Hz. So the output frequency for this inverter should be 50 Hz, which means the fundamental frequency is 50 Hz. The modulation technique is designed to eliminate the third and the fifth harmonics. So the output has no third or fifth harmonics. If we use an output C filter, okay, to eliminate the seventh and higher order harmonics, determine the filter capacitance value. We need to find the value for the capacitance, and the question gives us the load is a series RLC, and its parameters are as follows: 10 ohms, 31.5 millihenry, and 112 microfarad. How to solve this question? What we need actually is to find the output waveform. This output waveform is going to a load. This load is RLC load. We need to find the impedance of the load, okay, the impedance of the output waveform, and then compare it with the filter and make sure that our filter is able to eliminate all harmonics. Now let's first obtain the impedance of the output waveform. So first we need to find the what we call the inductive reactance for the nth harmonic. So XL is equal to how much? J times 2n pi times the frequency times L. So 2 pi FL, right? So here we can say that 50 Hertz times the inductance is equal to how much? 31.5 times 10 to the power minus 3. So this is J N 2 pi FL, or 2 omega L, right? Calculate this value, you'll find that this is equal to J 9.89 N ohms. So this is the reactance, the inductive reactance. Similarly, we can find the capacitive reactance. So XC is equal to how much? 1 over J omega N, right? So J times 2N pi times 50 times the capacitor value, which is 112 micro. This will be equal to how much? Minus J 28.416 over N ohms. Okay, now we can obtain what we call the impedance for the nth harmonic voltage. So Zn in this case is equal to how much? The magnitude, the root square of R square plus the XL minus XC, right? So this will be R squared 10 squared plus 9.89 N minus 28.416 over N. These are all squared. Now this is the impedance for the output voltage. Now we need to design our filter to be able to cancel the 7th and the higher order harmonics. Now the nth and the higher order harmonics would be reduced significantly if the filter has much smaller impedance than the load, and this usually less than 10 times. Now we can say that Zn, the impedance, must be larger than 10 times the capacitor value. So this capacitor must be much smaller than this impedance in order to be able to reduce the to eliminate the harmonics. Okay, now we can say that XC, the magnitude here, is equal to 1 over 2n pi times 50 times CF, the capacitor value, which is how much? 1 over 100 times 50 times 200, 100 times n times pi times CF, and this is the impedance or the reactance, the capacitive reactance for the filter. This value must be less than 10 times this value, must be less than Zn, right? Which is 10 squared plus 9.89 n minus 28.416 over n squared. Solve this one for the 7th harmonic. Once we eliminate the 7th harmonic, like once we design this filter to eliminate the 7th harmonic, the 7th and the higher order harmonic will be reduced, will be eliminated, because this is what is a low pass filter, right? The capacitor is a low pass filter. So once you reduce like the 7th harmonic, all the 7th, 9th, 11th, all the harmonics will be eliminated as well. So here for n equals to 7, this is the 7th harmonic, the capacitor value must be greater than 1 over 10 n pi times 10 squared plus 9.89 times 7 minus 28.416 over 7, is squared, and here finally CF must be greater than 68.96 microfarad. Okay, and this is the capacitor value, the filter value.